The problem is to find the geometric multiplicity of the eigenvalue lambda equal 4 for the given matrix A. Well, if we rephrase the question, what we're really asking is, what is the dimension of the eigenspace E4? Meaning, how many basis vectors does that eigenspace have? So we'll need to investigate the eigenvectors corresponding to lambda equal 4. To take a look at this eigenspace, we'll be solving the system a minus lambda I. In this case, lambda is 4, so I'm going to write a minus 4i for our coefficient matrix, and it's a homogeneous system, so all our constants there are 0. Setting this up, we'll be subtracting 4 from the diagonal entries of A. I like to do that first just to make sure I do that subtraction correctly, and the other entries of that matrix will be recopied. So there we go. That is a minus 4i, and we're looking at the homogeneous system. So we'll do some row operations and get this into our REF. Let's divide row 1 by -1. That just creates a 1 in the upper left-hand corner. And then we can take row 3 minus 2 times our pivot row. So that's going to give us 0, -3, and +3, and then a 0 in our bottom row. Top 2 rows won't be changing. Right, at this point we can move down and to the right. This -1 is going to be our new pivot, so let's take row 2 divided by -1. That's just going to change the signs all the way through there. We can recopy our top and bottom rows. And then last thing we can do is just clean up that second column. So let's take row 1 plus our pivot row, and we can also do row 3 plus 3 times our pivot row. So in the top row, that'll give us 1, 0, -1, and then a 0. That middle row won't be changing. And in the bottom row, we get a row of zeros. So now we've got our REF. Now to solve this system, we need to take a look at the leading ones. So in the first row, there's our leading 1. In the second row, there's our leading 1. So overall, we've got 2 leading 1s in this matrix. The third column does not have a leading 1, therefore it's going to take a parameter value. Alright, so at this point we should be able to predict the answer. There's one parameter in the solution, meaning there's going to be one basis vector for this eigenspace, meaning the geometric multiplicity of lambda equal 4 is equal to 1. So it's great to be able to make that connection at this point. If we can't quite see that yet, then it's fine to write out a few more details, actually go through it, solve the system, and then we'll see clearly what the geometric multiplicity is. What we're doing is finding eigenvectors. Normally they're called x, so it makes sense to call our variables x1, x2, x3 here. And we've said that x3 is equal to t. The top row tells us that x1 minus x3 is equal to 0. Meaning x1 is equal to x3, and that tells us that x1 is also equal to t. Middle row tells us that x2 minus x3 is equal to 0, meaning x2 is equal to x3, and we said before that x3 is t, so that tells us x2 is also equal to t. So if we write down what our eigenvectors look like then, they have the form TTT, or we could rewrite that a little bit more nicely as x is equal to 1, 1, 1 times t, meaning our eigenvectors are the non-zero multiples of the vector 1, 1, 1. Remember, technically the 0 vector is not an eigenvector. So that's why I say non-zero multiples. Fastest way of summarizing this is just to give a basis for E4, And we've just got that single basis vector there, 1, 1, 1. So to go back to our problem, we're asked for the geometric multiplicity of lambda equal 4. We said we could rephrase that as what is the dimension of the eigenspace E4? In other words, how many basis vectors does that eigenspace have? Well, we can see now there's just a single basis vector in that eigenspace, so the answer is 1. The geometric multiplicity of lambda equal 4 is 1. Let's put a box around that. That is our final answer.